Hey, Psych230 students, it's time for our week 8 Muddiest Points review. So this is our last Muddy Points review, and this one is mainly covering the chi-squared based on everybody's questions this week. So let's go ahead and jump right into that. So the first question we have here is, the muddiest thing about chi-squares is probably when and how to apply the test when interpreting the results. I think it can be unclear how the expected frequencies are calculated. I have to see it step by step. Example through WebAssign. And then the muddiest thing I learned from this topic was probably the actual chi-square equation. I just have to try to remember it because there are so many other equations for everything else. So first thing, just to kind of think practically about this. First off, you do not need to remember or memorize any of the formulas for this class. So again, all of the problem sets and the tests, you have access to notes. There's no reason really anyone needs to memorize the formulas. Most statisticians just use computer programs like Jamovi to do the calculations themselves. So the reason we use the formulas is partly to help you have a better understanding of how you end up with the numbers that you end up with. So I think it can be really helpful to have hand calculated things. So try not to, worry about memorizing. Also, this is just a tip for the final exam is, ideally, you have at least a sheet that walks you through the calculations for all of the test statistics we've learned. And this is partly because there's going to be that one 20-point question on the exam. And your task is going to be a paragraph describing the data and then a table of research, or a table of data, I'm sorry. And your task will be to figure out which statistic to apply. To do that, you're going to have to read the paragraph. You're also going to look at the data and determine which of the 7 test statistics should be applied. Once you figure that out, and there's a video, the final exam review video walks you through how to make those decisions. Once you figure out the right statistic, then you should have that sheet of paper at a minimum or a packet of materials for that specific statistic. And then you'll ideally have how you do a hypothesis test start to finish for that, any of your test statistics. That way, then you're ready for that 20-point question. So whenever I teach this class in person and they have an in-person test, they get cheat sheets, and typically just people will have one sheet that is, the per test statistic where it's just listed out how you answer it from start to finish. You already have some of that stuff in the notes, like the slides. You also can do it from the solutions to all of our problem sets. Those all kind of walk you through. The hypothesis test calculation videos also show you that. So that's where I really want to kind of get you ready for the final exam in terms of that, is just, be ready and, kind of try to separate your notes out by test statistic, by chapter, basically. And then this question about it's unclear how the expected frequencies are calculated. That is the key to the chi-square, because we're teaching you 2 different chi-squares. The one version, you'll calculate expected frequencies based typically on your hypotheses. And then the second one is a calculation more. And so that's where I want to direct you to. So I'm going to shift to, let's go to our resources. So if you go to resources for week 8, there's all the slides. And then here's the final exam review video. It's also under the final exam. So just so you know there, but it's this chi-square formulas sheet here. So this is essentially the setup for the 2 different chi-squares. So the goodness of fit test has this formula here for expected frequencies. So it's just, you're going to have the proportion times the total number of people. So what the proportion, that P, will typically come from your hypotheses, from the null and alternative hypothesis. So basically alternative will determine your P. Now, typically there's 2 ways to do this. One is where you're trying to determine essentially what we call a no difference hypothesis. So essentially, if you have two groups and you think that there should be no difference between these groups, and you have 20 people in your study and you're going to measure whether they're in group A or group B, and you have no hypothesis about there should be any specific difference, you should expect about 10 of those people to be in group A and 10 in group B. So how do we get there? Well, the P would be 50-50. 50% of the people should be in group A, 50% in group B, and so your P is 0.5. So you would just multiply 0.5 times your N, the total number of people, 20. 0.5 times 20 is 10. So you should have 10 in group A, 10 in group B. Those would then be your expected frequencies. And then you can see if there is a difference. Now, let's say you are still doing the same kind of no difference hypothesis. If you have 3 groups, and well, let's do 4 groups, that'll be easier. So let's say we've got 4 groups and 20 people. If we again assume that there should be no difference between our 4 categories, A, B, C, and D, well, we should expect 25%, or a quarter of the people in each of the groups. So that again is our P, our proportion, and so we'd expect 1/4 times 20, or 0.25 times 20, and you'll get 5. And so we should expect 5 in group A, 5 in group B, and 5 in group C, and 5 in group D. There's our 20 total people. So that's where, again, you have a no difference. You just have to then evenly split the proportions and then multiply that times the N. Now, the other possibility is that we could have a previously known kind of proportions, and that's where, based on previous data, it would be told to you in the question that we should expect, maybe it was 2 groups, and we should expect 2/3 of the people to be in group A and 1/3 to be in group B. Well, so then you can make your proportion for group A 2/3 times our 20 people. So that's 40/30, and so you're going to end up having a fraction of a person as part of your expected frequency for that group. And then you would do the same. It would be 1/3 times 20 for group B. And so in that case, the 2 groups would have different expected frequencies. Right? So that's, again, so it's important to know that this is what we're talking about right now is a goodness of fit test. So this is where we have only one variable. There's one thing and it has categorical outcomes. Okay? 2 groups, 3 groups, 4 groups, whatever it is, but it's just one variable. And then this is our expected frequency calculation. Also remember your degrees of freedom is calculated differently. But this chi-square calculation here, that doesn't change when we get to the chi-square test for independence. You'll notice it's the same formula. Okay, so let me just zoom out here a little bit. So these 2 formulas are exactly the same. What is different, though, is the degrees of freedom are different for the 2, and the expected frequencies are different. And so this sheet of paper would be really helpful because you first have to decide, are we doing a goodness of fit chi-square or a test for independence chi-square, and then you'll use the appropriate formulas. Now, the test for independence is a situation where you have 2 variables. Each of those 2 variables are dichotomous, or are categorical variables. And so how would you know this? How would you know whether you have 1 or 2 variables? Well, typically the description of the study will just mention one thing that was measured for the goodness of fit. And then you'll know you'll have 2 when you mention 2 different things are measured. But it's also often helpful to look at the data that you have. So there might be a table of data. And so let me jump up here to an example from the goodness of fit. So let's say you're given this data. So right here, this part right here is you've just got 3 categories. So whatever we're measuring here, it has 3 possible outcomes for people. And then what you see here are numbers in here. Now it often won't, the F sub O, which is our observed frequency, won't always be listed. It might just say 15, 19, and 6. What you see there is 1 row, 3 columns. That is a goodness of fit because the column is one of our variables. The row would be another variable, but we only have 1 row, so it doesn't have any other category. So there is no variable there. It doesn't vary. And so we just see 1 row of numbers and there's multiple columns. So in this case, 3, right? That would tell us that we're doing a goodness of fit test. Whereas when we get to the chi-square test for independence, let's see, and here's another just example of a goodness of fit. Here's one that we walked through. This is how people hung a picture. So we had a group of people, 50 participants, hang this picture. There were 4 different ways they ended up hanging it up. And so that's the data that you get. And so based on that data, we see just one row. That's a goodness of fit. But what could end up happening is we get something more like this, where we have 2 rows. So we see 4 columns and 2 rows. This kind of matrix look, this is telling us that there are 2 variables, and this is the test for independence. So what you see is over here on the left is one variable. It has 2 categories, introvert and extrovert. So this is our personality variable. And then this is people's favorite colors. And that's the second variable. And people prefer red, yellow, green, or blue. So now we're looking at, and this is why it's called a test for independence, to see whether these 2 variables, personality and favorite color, are independent of each other or related or correlated to each other. Okay, so that's essentially what we'd look for. And then here, doing the expected frequencies is you get, so we've given this data here, and so I just repeated that down here. And then what you need to have are what we call these marginal totals. So you might be given what's just in the blue, and then the blue table would be filled in with the numbers. You might not have these numbers on the outside, so you would have to calculate them. And what they are just the totals by column and totals by row. So if we add up 10 plus 3 plus 15 plus 22, we get 50. If we add up 90 plus 17 plus 25 plus 18, you get 150. If you add up 10 plus 90, you get 100. If you add up 3 plus 17, you get 20. 15 plus 25 is 40. 22 plus 18 is 40. So those are what we call our row totals and our column totals. And then the total is just the total number of people. So you could add up 50 plus 150, or to verify, add up 100 plus 20 plus 40 plus 40. Now, we use those to then determine the expected frequencies. And so often it can be helpful to think of it like this, is that now we have our row totals and column totals, and now let's figure out, if we didn't know anything, if we didn't know where people actually were, and we looked at this data, we'd have to try to guess, okay, well, about how many introverts and extroverts like the color red? Well, we know 100 people like red out of our 200, okay? But we know that there are more extroverts than introverts, 3 times as many. So what we should divide this 100 is so that of that 100, 3 times as many like are extroverts as are introverts. So that's the kind of the thinking here, and just to kind of walk you through it. So if we think of this is 50 and 150, so it should essentially be 25% of the 100 should be introverts, and 75% should be extroverts, right? Because 50, so if you think about there are 200 people, 50 out of 200 is 1/4, 150 out of 200 is 3/4. So you can also think of it as 1/4 and 3/4. So then if we multiply 1/4 times 100, we get 25, and that's where we'd put in the introvert box. And then 75, because that's 3/4 times 100, or 0.75 times 100, is 75. And so of the 100 people who like red, we would expect 25 of them to be introverts and 75 to be extroverts. Why? If personality and color preference are independent, meaning that it'll be split up exactly as the numbers are split up. So that's kind of a long way around it, but here's how you just have to do it, is just use, so this walks you through all of those boxes of what I just talked about, but just use this formula. For each box, take the frequency for the column, that's the column total, times the frequency for the row, that's the row total for that box, and divide by n. So let's go back to that first box. Let's do it here. Okay, so for this box here, we take the column total, 100, multiply it times the row total, 50, and divide by our n, 200. And if you do that, it will come out as 25. To do this box, we take the column total 100, multiply it by the row total 150, divide by the n 200. Okay, so that's how we end up doing all this, and it gets us to all of these. This isn't doing it in that way, but that's what this would get us to. So this is one of the cells, and that's the formula that we want to use. So going back to our resources page, and then the chi-square thing, that's the expected frequency calculation. All right, so that's, again, where I would direct you. Definitely want to have that printout and use that. Okay, so hopefully that helped with a little bit of that. We'll come back to some of that stuff, though, I think. When it is appropriate to use it, especially when it comes to sample sizes. So this is, somebody's confused about when it's appropriate to use it, the chi-square, and when it comes, especially when it comes to sample sizes. I'm also a bit unclear on how to interpret the results in borderline cases where the observed and expected frequencies are close but still yield a significant result. So I'm guessing this is in reference to, let's go back to my slides here. Very end of the chapter, it talks about some of the assumptions of the chi-square, and one of the things that can happen is you can get chi-squares that sort of exaggerate differences when you have very small frequencies. And so we suggest that if any of your expected frequencies for any of the boxes are less than 5, then you probably shouldn't use the chi-square. It's just not, it's going to exaggerate a difference. And it goes through an example of how just one cell that's slightly off would end up with adding a lot to a chi-square. 9 is quite a bit of difference between the observed and the expected frequency. So what's happening here is that it's only a 3-point difference here between an expected frequency of 1 and the observed frequency of 4. But that actual observed frequency is 4 times bigger because 1 is such a small number. So when you have expected frequencies that are very small, it kind of exaggerates how much the difference is. Whereas, let's say the expected frequency was 21 and the observed frequency was 24. That is also a difference of only 3 people, but the amount of difference there in terms of a size is going to end up being a very small difference. So it won't end up being as big because the kind of percentage of difference isn't as great. So just, again, you're never going to have to worry about this. You're just going to have to do the calculations. But it is something just to be aware of, is that, if you ever had a chance to do chi-square like at work or something like that, yeah, if you've got small expected frequencies, you might get a chi-square and you might be interpreting your data saying, oh, there's a statistically significant difference here, and there isn't. Or it may not be because it's exaggerating that difference. But as long as you have expected frequencies of at least 5, we should be fine. Okay. So hopefully that helps with that. So yeah, and again, you shouldn't get large significant results if the observed and expected frequencies are actually pretty close. Because again, if you look at our formula here, let me go back to this. If you look at this formula, we're looking for a difference between the observed and the expected frequencies in the numerator here. And so if there isn't much of a difference, you're not going to have a very large numerator. But, and this is why the expected frequency size matters, but we also divide it by the size of the expected frequency. So if you have a very small expected frequency, less than 5, okay, that's where the proportion starts to become an issue. And so that's where we'd want to be careful with it. But if, again, as long as you don't violate that rule of having any expected frequencies less than 5, all your expected frequencies are at least 5, then any differences, even if they're small and you end up with a statistically significant result, then I think you can fairly interpret that as being unlikely to be due to chance, and that there is actually probably some kind of difference, or maybe some kind of relationship between the two variables. Okay, and then last couple here. What I find most confusing is distinguishing between the chi-square test for independence and the chi-square test for goodness of fit. I find it challenging to remember when to use each type, especially when it comes to interpreting and setting up hypotheses for different scenarios. Another one is I struggle with trying to figure out when to use chi-square for independence versus chi-square for a fit test. I'm half assuming it will become clear as I do and redo the next two problem sets, but as of now I'm confused as to when to use one chi over the other. Okay, so hopefully I've already answered that, but it really comes down to goodness of fit. You only have one variable, so you should have one row of data, one row of frequencies, and that's it. And then maybe 2, maybe 3, maybe 4, maybe 5 columns. That's a goodness of fit test. The minute you have multiple rows where you have frequencies in those rows, that's when you have a test for independence. And then there was also something in here. What was it? Oh, the hypotheses part. Don't worry about the hypotheses. I really, at this point, I mean, when you get into these hypotheses, they can be pretty confusing. And let's say we're here, like, this is where goodness of fit, we're talking about different hypotheses. This is just trying to help you understand that we can use the chi-square for different kinds of predictions. But don't really worry about it. You're not going to have, I guess I'm really kind of not emphasizing hypotheses as much as we did when we were first learning hypothesis testing. It is important to make hypotheses, and the whole point of science is to make predictions, which are hypotheses, and then test those and see what the data tells us. So that's why hypotheses are important, but your need to get them exactly right and word them the right ways and things like that is not as important at this point. So that's why they're kind of de-emphasized. So you don't really have to stress as much about those kind of things like on the final or anything like that. Okay, so that's kind of it for these muddy points. I think I've hopefully covered everything. Again, if I haven't, let me know, reach out to me. Couple things with the end of the class here. One, I'll give you a little bit of help, because for those of you who are watching this video, that's great, is that on the final exam, I'm going to test the test for independence chi-square. And so be ready for that one. It's sort of a good way to kind of make sure that you're understanding chi-square. It's the little bit more complicated one, but that's the one that's going to be tested on the final exam. The other thing that I'll mention here is that also, if you would, please definitely fill out your student evaluations. I definitely care about those, look at those, use those to try to improve the class. It's been a little while since I've taught a fully online version of this class, so I want to get your feedback on that. And then the class technically ends today/tomorrow. And so I will, it's definitely okay. I have to get grades in by Monday. So it is okay if you need a couple extra days and you need to get things, if you can get things into me by Saturday, that can also absolutely work. Because I'll be spending this weekend catching up and grading and then getting all your grades done and ready to be submitted by Monday. Otherwise, it's been a pleasure. Hopefully you got a lot out of this class, and otherwise, good luck on the final exam. Thanks.